Okay, so here we will talk about the displacement current. Yeah, the displacement current in Chinese called 位移。位移电流啊，位移电流。So displacement current. Okay, so here it says if you compare the two terms on the right side of the equation, ampere Maxwell, so you will see that the product, this one, epsilon naught times d phi e dt must have the dimension of the current. So let me go back a bit to show you what it mentioned about. So here it says this one on the left side is the line integral, and on the right side it is something like mu zero times the current, mu zero times the current. So this one is a current, and then for the second term we also have a mu zero times another term. So this term should have the dimension of a current, including the epsilon naught times d phi e dt. This is what it mentioned. Okay, this term epsilon naught d phi e dt must have a dimension of a current. So in fact, that product has been treated as being a fictitious current called the displacement current, ID, and then so we call it ID. The displacement current is this expression, and in that sense, if we define this term to be ID, then the ampere Maxwell's law can be written as the left side is still the line integral, and then on the right side we have two terms. The first term is mu zero I enclosed. This is the real current, actually the practical current, and then for the second term mu zero times the displacement current, also enclosed by the Ampere's loop. Okay, so where ID enclosed is the displacement current enclosed by the integration loop or the Ampere's loop. Okay, so so actually what does it mean? Actually the displacement current is actually like the current going in the capacitor. So we can just try to elaborate it a bit. So this ID is epsilon naught d phi e dt. So now if we consider is a parallel plate capacitor, then we can have something like C equals epsilon naught A over D, if you still remember in chapter 25. We have C equals epsilon naught times A over D. A is the cross section, D is the spacing between the parallel plate. Okay, so here with the phi e we can make it like epsilon naught times d e times a dt. So phi e is the e times a, because for the parallel plate capacitor the E field is also uniform within the parallel plate. Okay, so the A can be factored out, so we have an epsilon naught A times dE dt. And then as much as E is uniform, we can also have E we can actually have E equals E equals V times D, or V equals E over D, or V equals is the other way around. It should be V equals ED, or So as much as we have a V equals E times D, so actually we can just multiply a D inside the derivative, and then also divide the D outside. So actually we can just we only multiply D inside and then divide a D outside. So now you can see this is nothing but the capacitor. So we can see this is the capacitor, and then times dV dt. Okay, so here we have ID. So here we have ID equals C dV dt. So which is actually the same as the equation for the capacitor, ID equals C dV dt. So you can also imagine this displacement current is also the current going out the capacitor. Okay. So here it's also mentioned about the displacement current. Finding the induced magnetic field in chapter 29, we find that the direction of the magnetic field produced by a real current. By the right-hand rule, we can apply the same rule to find the direction of an induced E field, a B field, by a fictitious displacement current ID. So then, as done previously, the magnitude of the magnetic field at a point inside the capacitor at radius r from the center is this expression, and outside is this expression. Okay, so actually we don't try to go through it again, because in chapter 29 we actually have derived these two equations. When you consider, maybe I can just go there to find where it is. You can just actually here we already derive this equation. So when you have a wire with a static current going out of the page, it will generate B field. So for the B field inside the wire, it should satisfy this one. It is proportional to the radius, and for outside the wire, it is inversely proportional to R. But here, the only different thing is that we replace the current into the displacement current. This is the only difference. So when you consider the capacitor, and then so here we only have a displacement current. This I is the displacement current, or we can consider here is the displacement current through this capacitor. So it's somehow like this is the current, this is the current. Actually there's no current going through it, but you can imagine there are some displacement current which is a frictional current, frictional current or fictitious current going through this capacitor. And then using the Maxwell's law, then you can determine the B field generated by this fictitious current, or the displacement current ID. So we have mu 0 ID times over 2 pi r squared times small r. For this part is inside the plate, inside this area, and then when you consider the part outside the capacitor, then it is inversely proportional to the radius. So this part is for the outside the capacitor. This is inside the capacitor. This one and this one. So up till now, any questions? Okay, so yeah, here we have another sample problem. So here it says the circular parallel plate is being charged with a current I between the plate. What is the magnitude of B dot ds in terms of mu 0 I and at the radius small r, which is capital R over 5 from their center. Okay. So here we have the closed line integration of B dot ds equals mu 0 I d enclosed, the displacement current. Okay. So, and here we assume that the current is uniform. The current is uniform. So here we have a ID enclosed over the whole ID should be pi r square over pi capital R square. So here we assume that the ID is uniform. The ID is uniform. So in this case, we have a ID enclosed should be ID times pi r square, or actually the pi and pi can be cancelled. So we have a small r square over capital R square, and then we can put this one back to here. So we have integration of a B dot ds. This is what it asks for. So we don't need to evaluate again. So so we have a mu 0 times ID times small r square over capital R square. Okay, and here what we need to find is a small r will be capital R over 5. So here it should be mu 0 times ID, and then here capital R over 5 quantity square over R square. Okay, and in this case we have a mu 0 ID over 25. Or we can just put it as a small I, because here it just give you the I here, so we can just ignore this D, or maybe I can just ignore this D here, ignore this D, yeah, something like this will be fine. So this is the answer, mu 0 I over 25. Okay, so for part B, it asks you in terms of a maximum induced magnetic field, what is the magnitude of the magnetic field induced at R equals capital R over 5 inside the capacitor. Okay, so and as much as we know, B of R should be proportional to R when we consider R is smaller than capital R. So which will be mu 0 ID and then over 2 pi capital R square times R, when we consider the R is smaller or equal to capital R. Okay, so which means that B max is actually B of capital R, which means it is mu 0 ID over 2 pi capital R, 2 pi capital R, because here R is capital R, so cancel one of the order. So in this case, BR of B max would be B of capital R over 5, and then B max is B of R, so it will be mu 0 I d over 2 pi capital R square, and then this is R over 5. And then here we have a mu 0 I d and then 2 pi R. So it means it is 1 over 5, because yeah, actually it is nothing but yeah, BR is proportional to R. So when we consider R, small r is capital R over 5, it should be 1/5 to the maximum value. So actually the calculation in this chapter is not so difficult, because most of the calculation should have already been introduced in the past chapter. So here in chapter 32 we only try to conclude the Maxwell equation, and then of course we need to introduce the idea of a displacement current related to the Ampere's law or the Ampere-Maxwell's law in this textbook. Okay, so here, so this is actually the Maxwell equation. So the four fundamental equation for electromagnetism called the Maxwell's equation are displayed in this table. So we have a Gauss law for electricity, Gauss law for magnetism. So you can see here E dot dA, B dot dA equals Q enclosed over epsilon naught. This is 0. So we relate the net flux to the net enclosed electric charge, and then we relate the net flux to the net enclosed magnetic charge, which is 0. And then here we also have a Faraday's law and Ampere-Maxwell's law. So this is the induced EMF equals the negative of the rate of change of the magnetic flux. So we relate the induced EMF, induced electric field, to changing magnetic flux. So here we have a line integration of B dot ds, which is, this one is the displacement current, this is the normal current. So we relate the induced magnetic field to changing electric flux and to current. So here it says, this equation are written on the assumption that no dielectric or magnetic material are present. So in chapter 25, where we have actually considered the dielectric. So in that case, the epsilon naught will be changed to the epsilon, something like epsilon would be epsilon naught times the kappa of that dielectric. And of course there are some magnetic material, so yeah, generally you can write it as a mu epsilon, mu here and then epsilon here. So the mu naught epsilon naught only occurs here. So when there is when the material does not include the magnetic or dielectric material, then we only use the mu naught epsilon naught. Okay, so these four equations explain a diverse range of phenomena. They are basis of the functioning of such EM device as electric motor, television transmitter, receiver, telephone scanners, radio, and microwave oven. So actually in the electromagnetism there are some other equation, but actually using the Maxwell equation would be sufficient to solve for all the problem. And especially nowadays we won't try to use hand calculation for most of the problem. We try to put it in the computer using something called a finite element method to solve for the solution of the equation. Actually in these textbooks it only tells you this is the integration form of the Maxwell equation, Actually, after the slides of this chapter, I will have the supplementary notes about the Maxwell equation. I will tell you what is the differential form of the Maxwell equation. So we can convert this 1, 2, 3, 4 equation into the differential form of the Maxwell equation. And actually, for the computer programming, rather than calculating the integration, it prefer to calculate so-called the partial differential equation (PDE). Of course, in previous chapter, I already tell you how to solve for the constant coefficient ODE, and actually, solving some specific type of PDE will not be so difficult. Will not be so difficult. You will still be able to solve some simple PDE, but of course, generally, PDE is not easy to solve. But at least the Maxwell equation is linear. So those PDE is solvable, and actually for the next chapter, chapter 33, we will try to solve the Maxwell equation in a specific condition called the free space condition, and then using the Maxwell equation in free space, we can actually derive the wave equation, and then when we solve the wave equation, the solution will be the electromagnetic wave. Actually, in the textbook, it does not tell you lots of the reason or how the equation are derived, but actually I will actually load it in the supplementary notes. So yeah, so this is pretty much it for the Maxwell equations. Okay, so for the remaining of this chapter is what I call is the hardcore physics stuff. So just feel relaxed to listen to the stories. Okay, so this part is about the magnets. Okay, so actually this page tells you the magnetism of the Earth. Okay, so actually for the Earth, we have, yes, I suppose you know, for the Earth we will have a North Pole and South Pole, and usually that North Pole and South Pole usually refer to the geometry South Pole or North Pole. Yeah, and of course you know for the geometry North Pole and South Pole, which will be very cold. And actually here this North Pole and South Pole refers to the geomagnetic North Pole and South Pole, which is a little bit different from the geometric North Pole and South Pole. So actually here for this R-axis is the geometric North Pole and South Pole. This is North Pole, this is South Pole. And this M refer to the geometric South Pole and the geometric North Pole. So actually the geomagnetic North Pole and South Pole. So actually the geomagnetic North Pole is at the South Hemisphere. So it's opposite to the geometric North Pole and South Pole. So for the Earth, the South Pole of the dipole is actually in the north. Okay, so it says Earth is a huge magnet. So for point near the Earth's surface, its magnetic field can be approximated as the field of a huge bar magnet, a magnetic dipole that straddles the center of the planet. And then figure shows here is the idealized symmetric depletion of the dipole field without the distortion caused by the passing charge of a particle from the sun. Actually, we don't actually know how the Earth can generate the magnetic dipole, but actually the magnetic dipole is very important to the human beings. Without the magnetic dipole from the Earth, all of us would probably die. Probably die. And yeah. And actually, in the solar system, there are not so many planets with the magnetic dipole. One of the planets is the Earth, and another one I'm not really sure is the 海王星. Actually, I'm not sure whether it's the Neptune or what. Okay, but not so many planets have the magnetic dipole. But it will be very important. And you can imagine, so many of the high energy particle are so-called the charged particle, like the gamma ray or X-ray. They're charged particles. So suppose the charged particle is shooting to the Earth. It's shooting to the Earth. I'm not sure whether it's positive charge or negative. Just assume it is a positive charge. For negative charges is similar. The direction is the other way around, but it is it has the same meaning. So you can imagine if a charge is shooting to the Earth, and if you still remember, there will be Lorenz Force. Lorenz Force. We learned that in chapter 28. So if you still remember, the Lorenz Force is actually F equals QV cross B. QV cross B. Okay, so the V is the velocity of the charged particle, and the B is of course the B field. So here, okay, so here suppose the B field is pointing upward. So the B is shooting to the Earth. So V cross B is something like V cross B. So the F will pointing out of the page. Okay, so F is pointing out of the page. So this will make the charged particle going this way, and then won't shoot to the Earth. Okay, so that's how the magnetic dipole of the Earth can save us from the high energy particle, so-called the high energy particles. Okay, yeah. And actually, for the magnetic dipole, there are some weak points. Actually, there are some weak points, which is actually the geomagnetic north pole and south pole. Geomagnetic north pole and south pole. So you can imagine if the charged particle is shooting from here. Okay, so here the magnetic field is actually opposite to the velocity. This is V, and then B is pointing to the opposite side. This is V, this is B. So V cross B is V cross B times equals V times B times sine of theta, and this theta is almost 180 degrees. For 180 degrees, sine of 180 degrees is almost 0. So there's no force acting on this charged particle. So this charged particle will directly shoot to the Earth. And similar for that case, this theta is almost 0 degrees. So sine 0 degrees is also close to 0. Okay, so this is two weak points, and actually, for those two weak points, we can actually see this phenomenon called the aurora. Aurora, which mean in Chinese it is called 极光. Okay, so for the northern part of the European or maybe in South America, so for those places, you may be able to observe the aurora, but yeah, of course it is not so good for us because those kind of high energy particle will make you have a higher probability to get the cancer. So yeah, so actually the magnetic dipole from the Earth is really important to us. And in this paragraph, it just tells you that yeah, there are some declination angle between the geomagnetic poles and the geometry poles. So the poles axis MM makes an angle of 11.5 degree with the Earth's rotational axis. The south pole of the dipole is okay. So this is the magnets from the Earth, the magnetism of the Earth. Okay, so here is the really hardcore stuff, which actually relates to the quantum mechanics. Maybe in high school chemistry you may have read some of the equation, but yeah, it's really hard to explain what it is because it really relate to the phenomenon of the quantum mechanics. Actually, to get this equation, you need to solve the Schrödinger's equation considering the relativistic effect. So actually I don't know how to solve those things. Even for the Schrödinger's equation with something like the hydrogen potential will be sufficiently difficult to understand. Yeah. But yeah, actually in chapter 38, I just explained how to solve the Schrödinger's equation for some simple cases like the potential barrier or tunneling effect, which is already quite interesting. So if you have interest, you can just check my channel. So let's come back to here. Is mentioned actually for this section, it just try to mention the fundamental unit of the magnetism, because for the charges we can try to separate the positive charges into smaller and smaller one, and the elementary charges will be the electron or the proton. Proton has a positive charge, and then for the electron it has a negative E, the elementary charge, still the elementary charge. But here we have not talked about what is the fundamental element of the magnetic dipole. So here it tried to mention how should the magnetic dipole, or how should the magnetic field exist. Okay, so it says an electron has an intrinsic angular momentum called the spin angular momentum. So it says for electron it has intrinsic in Chinese is called 内在, which means that it's not possible for you to observe the rotation of the electron because the electron is so small to observe. But the point is that this rotation should occur. Otherwise, actually we observe some other things called the magnetic dipole moment, and if this exists, it tells you that the electron should rotate to generate this momentum. And that's why we call this electron has an intrinsic angular momentum, because we cannot really observe it, but if we don't exist, we cannot observe these things. But actually we observe these things. So when you're going back, then the electron itself should have some intrinsic angular momentum called the spin angular momentum. And of course, this angular momentum is due to the spin of the electron. Okay, so S associated with the spin is an intrinsic spin, magnetic dipole moment, mu s. Okay, so by intrinsic we mean that S and mu s are basic characteristic of an electron, like its mass and electron range, electric charge. Okay, so it's just like the mass. When I'm here, I have mass. Yeah, you cannot remove the mass, this property from me, because when there is an object, then there must be a mass. So as this spin is also an other intrinsic characteristic of the electron. Okay, so vector S and mu s are related by this equation. So mu s is the dipole moment, and capital S is the spin. Capital S is the spin, and then it is proportional to the elementary charge, and then normalized by the mass. So actually, this equation is actually come from the quantum mechanics. And you can also imagine this is the elementary magnetic dipole. Okay, so as much as E is the constant, E is the elementary charge, m is the mass of the electron. So this is just nothing but a constant, And then we have the spin. And then this spin is quantized. We have so-called this ms equals h over 2 prime. H is so-called the Planck constant. 6.63 times 10 to minus 34 joule second. Okay, and I suppose you will have learned this in high school chemistry class, which is the spin. It can only be plus or negative half. So this is so-called the quantum number of the spin. So this number can only be a plus or negative 1/2. And this is actually h, the Planck constant. And of course, in quantum mechanics, we usually introduce another constant called the reduced Planck constant, h bar, equals h over 2 prime. So this one is called the reduced Planck constant. Okay, so in this case, we can just write it as a ms times h bar, and ms can only be a plus or minus half. And actually, this is the spin of the electron. And substituting this one into here, we can get the dipole moment. And actually here it tells you that this S with a subscript Z, because S is actually can be in any direction, but when we try to observe the spin, we can only observe it in one of the dimensions, just like the Z direction. And when we try to observe this S, and it turns out to be quantized into plus or minus 1/2. So it's very strange. I don't know why to explain this, but yeah, it's only related to the quantum mechanics stuff. Okay, so here. So here, when we try to plug in this one into here, we will get this expression, mu s z equals this E times h over 4 pi m, and we call it the Bohr magneton, which is actually the unit of the magnetic dipole, something like the elementary charge, and this is the magnetic dipole generated by the unit magnetic. And this one is actually 9.27 times 10 to minus 24. Okay, so this is the Bohr magneton, which you can comparing with it to the elementary charge, but this is for the magnetic field. Okay, so yeah, so when we try to put this one into the external B field, then there will be some potential energy. So this is nothing special. Okay, so this is another type. This is called the orbital magnetic dipole moment. So the electron not only spin itself, it also rotates across the atom, or maybe the nucleus is at the center, and then it will rotate around it. So when it is an atom, an electron has an additional angular momentum called orbital angular momentum, L, and then associated with the ORB, the orbital. Okay, so it has some similar expression, E over 2m, and then times this LORB. And then this LORB is related to another quantum number. ML is 0 plus or minus 1 plus or minus 2, ... Yeah. So actually in high school chemistry, probably you have learned 4 types of a quantum number. And then one of it is the spin, one of it is the spin plus or minus half. And then at that time you need to write something like a 1s, 2s, 2p, something like that, and then you need to solve something like that. This is plus half, negative 1/2, and then okay, so on and so forth. Yeah, so yeah, so we have some similar expression, but yeah, still I don't know how to explain it, but yeah, it's just something like the hardcore physics stuff related to the quantum mechanics. So we have some similar equation like that. But yeah, for the previous one, it relates to the spin of the electron, and for this one, it relates to the orbital angular momentum. And these two mechanisms will generate the electric field. The magnetic field. So you can simply imagine why the Earth can generate the magnetic field is that for the Earth, inside the Earth, we have something called the lava, and there are some charged particle or some metals. So in this case, as much as the Earth is rotating and also rotating around the sun, then in that case, all those charged particles, the motion of the charged particle will generate the magnetic field for the Earth. Okay, so let's stop here today.